Moving on to the integral calculus, it's much different than the differential calculus. And because in the previous section, we had some tools that we could use to differentiate anything we can write down, pretty much. But with integral calculus, it's usually the opposite. Most things you write down will not have a nice, just analytic way to go and solve it. So integral calculus is more nuanced. And we denote, so the integral of a function f, we often make it into a capital F and call it the antiderivative. And it's defined to mean that capital F is a function where you take the derivative of capital F, then you'll get lowercase f. These functions all differ by a constant because the derivative of a constant is 0. Then the antiderivative is really a collection of functions that all differ by some constant. Integration also distributes well over a plus sign, and you can pull constants out. So remember that. The fundamental theorem of calculus is the thing that links derivatives and integrals together. And it says that if you want to take the area under a curve, making that a negative sign if it goes below the x-axis, then all you need to do is take the difference of the antiderivative at the two endpoints that are bounded by some vertical lines. To see how this makes sense, you can first think of capital F as an area function, and then take the difference of the area up to the point x plus h and the area up to the point x, and you get this red region. Then, so now you're going to take a derivative of capital F. So you want to divide by the difference in x plus h and x. You divide by this width of the rectangle here, and you get something like the height of the function. So that's saying that the derivative of the area function is equal to the function. This is the gist of the fundamental theorem of calculus. Then the two rules we talked about earlier for differentiation become rules for integration as well, although they don't always apply. The product rule will become what's known as integration by parts. And these two bottom lines are the formula for integration by parts, but they're not the easiest to remember. So I want to give you a little way to remember how to get the formula and hopefully to understand what it's saying better as well. You start with a product of two variables, u and v. You can write it as the integral of the differential because those cancel out. Use product rule on the differential to get u dv plus v du, and then you integrate over the plus, and it distributes. Finally, you subtract off the integral of v du from both sides, and here I've switched the left and right hand sides to get it into a formula kind of form. Oftentimes, when you use integration by parts, you want to evaluate between two bounds. And to do that, you just evaluate all three parts between those bounds. The integral from a to b of u dv is equal to the product of u and v when you find the difference of the product at the values b and a, and then subtract the integration from a to b of v du. For exam P purposes, you will often only need to use when u is either x or x squared, and often also v will be a function like e to the minus x. So in section 6, I put down a reduced form for how to find the integration of a product with e to the minus x and some polynomial, often just x and x squared. So you can use this formula. I'll talk about that in the next video on exponentials. The chain rule will become what's known as U substitution. And so we're going to use that capital F is the antiderivative of little f. And the chain rule says basically this. When you implement the chain rule, you're going to want to decide what f is first, and then you have some inside function g. If it works out, then you'll have, when you take the derivative of little g, it will be just resting out there on the outside, and you can separate the little f and g prime and just put it in this form so that when you integrate, you can just put in the capital F and evaluate over g. So you can think of it as evaluating from x values, a to b, of the composition f of g, or you can think of it as evaluating the capital F across the values g of a to g of b. Just as we did with FOIL in section 3, we generalized it to a product of sums of several terms. We can translate that over to integrals, which shouldn't be too surprising because the integral sign is meant to look like an S. It stands for sum. It says the product of two integrals is equal to the double integral of the product. And that is going to be over this region as x ranges from a to b and y from c to d. That region is a rectangle in the xy plane. We can also integrate over other shapes. And so, for instance, if you have a square and a triangle stuck together, something like this, and we'll do an example on how to integrate something like this. If you're wondering about my shirt, the artist intended this to mean that dinosaurs were figuring out how to divide by 0 around the time of the comet. And so that would have really helped their calculus, I'm sure.